All right. Hello, everyone, and welcome to the last solution session. Today, I think we also have the here. I can hear myself much better right now. So, okay. So let's get down to the problem set from today. The easiest task today was the task sleepless. And the lesson here with this task is whenever you see a problem statement that has something to do with dates and times, it is usually worth the time to slow down, to read carefully, and to make sure your implementation works on the first attempt, because debugging such a program is really nasty. And the general rule of thumb is try doing as much as you can with timestamps. So in our case, the input is given in hours and minutes. So the smallest unit with which you have to compute are minutes. So what we will do, we can separately take each of the times and change it into the number of minutes past midnight. So, for example, if we have the time 12:47, this will be changed to the integer 47. If we have another time 3:10, this will be changed to 3 times 60 plus 10, and so on. So right now we don't have time anymore. We only have a single integer representing a moment in time. What we can do, we can subtract those two integers. And in case the difference is strictly negative, we add 12 hours. So this is 12 times 60 minutes. And in this way we will get the difference between those two times. And this is what we then output as hours and minutes. Another useful thing when dealing with times and dates is knowing the manual for scanf and printf in C, C++. For example, you can use the format string %02d to print out a number with leading zeros and adjust it to the width of 2. So this is a really easy way how to format the output in such cases if we need to. All right. I believe no questions about this one. Probably the second easiest task today was the task with the missing number. So in this task we are given a string of digits. And what we are looking for is the smallest number that doesn't occur anywhere in this string of digits. So the first idea of a solution would be, is the number 1 somewhere? Yes, it is. Is the number 2 somewhere? Yes, it is. Is the number 3 somewhere? And so on. And as the length of this string can be up to 100,000, clearly we cannot afford to make too many such checks, because we would run out of time. So the question is, how large can the answer be? Now for some maths, what we have to realize is that, for example, if we consider 6-digit numbers, then there's quite a lot of these. We got 9 possibilities for the leading digit because it cannot be 0. And we've got 10 possibilities for each of the next ones. So this is 900,000 6-digit numbers. And we only have a string of length 100,000. And if we consider the substrings of length 6, there is only n-5 of them if the length of the string is n. So clearly there's more such numbers than 6-digit substrings in the string. And this means that the answer will always have at most 6 digits. There will surely be such a number that doesn't occur anywhere in the string. So the only thing we now have to do is we have to look for answers between 1, 2, 3, 5, 6. 1, 2, 3, 4, 5, 6. I skipped the 4, yeah. All right, that would be a stupid mistake to do in the contest. All right, so what we will do in our solution, we will take the input string. We will take all substrings of length 1 through 6. There are at most 6n such substrings. And for each of them, we convert it into a number and store the number into a set that this number is present somewhere in the string. So this is done in n log n time. And then we can simply traverse the set, and in a linear way we can find the smallest number that is not present in the set. And this number is the answer. What was actually harder about this task than solving it was my task when generating the test data, because of course, when I'm a problem setter, I'm trying to be nasty, so I'm trying to create the test data in such a way that the answer for some test cases will be really large, so that I will surely make the naive solutions time out. How to do this and whether this is possible? This is actually related to a cool mathematical fact which was first found by the Dutch mathematician De Bruijn. And the fact looks as follows. If you pick any alphabet, let's call it sigma, and if you pick any length of a string, let's call it k, then there is always a cyclic string. So you can take the letters of sigma, you can place them onto a circle, and the circle will have such property that each k-digit substring occurs exactly once somewhere on the string. So this is like zero redundancy way of listing all the substrings. You can imagine if you for example, have a safe with an electronic lock. So this lock has several digits, and you have a keyboard, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. You can type on this keyboard, and as you are typing, the digits are appearing here and they are shifting to the left. So each time you push a digit, it will appear here, and the previous ones will shift one position to the left. So in order to open such a safe, you need to generate each of the combination of digits if you are opening it by brute force. And this De Bruijn word, the Bruijn sequence, will give you the optimal way to do it. And it always exists. And the proof is actually quite nice. And it is based on graph theory. So what you can do, for example, imagine that the alphabet are the digits, 1, 2, until 9. And k is equal to 3. So we want to find a string that contains each 3-letter substring, 3-digit substring exactly once. What we can do, we can build a directed graph where each vertex will be a pair of numbers, for example, 4 and 7. And from each vertex there will be as many outgoing edges as we have the digits. So in this case 10 edges, each of them labeled with a digit. And if you are in the vertex 47 and you press the digit 3, you will get yourself to the vertex 73. And from here, if you press the digit 0, you will get to the vertex 30, and so on. So in this case, each edge of this graph corresponds to one of the substrings. So these are the first k-1 digits, and this is the last one in the substring. And as you are traversing this graph, you are visiting new and new k-tuplets of digits. So what you want to do, as you want to see each of the k-tuplets exactly once, you want to find an Euler path in this graph. And this is always possible because the graph is clearly connected. You can get from any vertex to any other vertex by simply pressing those numbers in order. And the in degree and the out degree of each vertex is exactly 10. So in such a graph, the Euler path always exists, and it can be efficiently constructed to construct such a word. And this was done to create the test data for this task. So I generated a string of length 100,000, for which the smallest non-present string is somewhere along 99,000. And I believe this is close to the optimum, that you cannot do a much better test case for this task. All right. Now, the third task, let's say in the order of implementation difficulty, would be the book stack. But this task is pretty tricky to get the right idea. So First of all, I'll explain a solution that uses a linked list. And then I will explain a solution that doesn't use a linked list, and it's really easy to implement in C++, for example. So the general idea looks like this. So what we have is a stack of books, and we can represent it one possible way as a linked list. So what we need to do, what we need to know about the stack of books are some pointers into the stack so that we can do each of the operations in constant time. And in this case, what we need is a pointer to the head of the list so that we can add new books onto the stack and we can remove books from the top of the stack. And also what we will need to do, we need to be able to flip the top k books. So in order to do this efficiently, what we will do, we will store 2 pointers to the books that are currently in depth k and depth k+1. So this is the place where we will insert the robotic arm and we will flip this part. And the main trick here is that usually if we implement the linked list, we call the 2 pointers to the neighbors, the previous item and the next item. In this case, it is better not to confuse ourselves to call these pointers just neighbor 1 and neighbor 2. So in order to implement the flip in constant time, what we will do is we will take a pointer to this vertex. So this is the place where approximately we are doing the split. We will take a look at both of its neighbors. We know which one is the correct one. So we can break these links, and we can make this one point here, this one point here, and this will be the new top. So again, we update the pointers. So the top pointer will be pointing here, the k pointer will be pointing here, and the k+1 pointer will stay pointing here. So in this way, with the linked list, we can implement each of the operations in constant time. Adding and removing is easy, and with these 2 pointers, we can also do the flip in constant time. So this was one possible implementation. It is easier to come up with, but harder to implement, to get everything right, because when you start using pointers, it's very easy to forget to update one of them, and it's hard to debug such a solution. So now for the trickier one. So let's see what we have. We have a stack of books, and there is the interesting part, the top k books, and then there's the bottom of the stack. And this bottom behaves exactly like a normal stack. So if we add new books somewhere at the top, the new books are at the same time added to this bottom part. And once again, in order to make this bottom part shorter, we only can remove books from the top. And again, this removes books from the top of this part. So in order to store this part of the stack in our program, we will just use a normal stack. And what happens here? Here we need to add and remove items at one of the ends of the sequence. But we can also flip the sequence and then work with the other end. So in order to do this efficiently, we will use a double-ended queue plus one Boolean flag representing which of the ends of the double-ended queue is currently on the top of the stack. So in this case, all operations are really simple. Flipping the top k books just means to flip this Boolean flag, and adding and removing books is done by operations with the double-ended queue and the stack. And this leads to a code that has like 10 lines of code only, and it's really simple and fast. All right, any questions? Okay. So what was next? Okay, the next task is also reasonably easy, are the dominoes. So what we are given is a rectangular board. One cell is missing, and we have to find out whether the rest can be covered by dominoes, and if yes, then we have to produce one such covering. And so now for the first part, which will be purely mathematical, let's find out when is it possible to cover the board. So first of all, we need to realize that each of the dominoes will cover exactly 2 cells. So after the cell is removed, the number of cells must be even. And this is only possible if both dimensions are originally odd. Because only in this case the total area is odd, and if we remove the cell, then we will get an even area. This is a necessary condition for the solution to exist, but it is not a sufficient condition. Why is it so? Because, for example, what you can do is you can color the rectangle in the standard chessboard fashion, and now you will know that if both dimensions are odd, then all 4 corners will be of the same color, and this color will have a majority by 1. So in this case, this is a small 3 by 3 rectangle. We have 5 black cells and 4 white cells on the chessboard. And in each possible case, there will be 1 more black cell if we color the corners black. Now what happens if you place a domino? The invariant is obvious. The domino will always cover 1 white cell and 1 black cell. So in order for the tiling to exist, the number of white cells and black cells must be identical. In other words, the missing square must be black. We can check this easily at the beginning of the code by comparing the parity of the 2 coordinates. So both coordinates of the missing cell must have the same parity in order for the solution to exist. And now such a solution always does exist in this case, so this is actually both a necessary and a sufficient condition. So if we check the parity of the dimensions and the parity of the coordinates of the missing cells, the solution will then always exist. Why is this so? So now for one nice way to... There are actually multiple ways how to create a valid tiling if it exists. And one of them can both easily be implemented and easily be seen that it is correct and leads to a proof that it always is possible. What we will do is, while the board is large enough, we can surely find one of these 4 directions in which the cell which is missing is not at the boundary. Actually, what we are looking for is a strip of width 2. Because we can easily tile a strip of width 2, right? We can just take the dominoes with the dimension 2 in the correct way, and we can place them next to each other. So what we will be doing is we will be looking at the board from the input, and we will start from the top, then from the bottom, then from the left, then from the right. And each time we can greedily cut away such strips while it is possible. So when it is not possible anymore, there are only 2 possibilities. One of them is we end it with just the missing cell and we are done. The other possibility, when we cannot cut anything more, is a 3 by 3 square with the missing cell exactly in the middle. And if we get to this situation, we then add the 4 remaining tiles like this, and we are done. So this is one possibility to do the tiling, and for this one it is immediately obvious that it works. The other possibility is that it actually, a simple greedy algorithm works. We can start in the upper left corner, process the cells one by one, and each time we discover an uncovered cell, we can try covering it with a horizontal domino, and if this is not possible, then we will use a vertical domino. This actually works. It is a bit nasty to prove that it always works, but it does. And so somebody could get lucky by simply guessing that this will work. And then the last part of this problem, which was basically an implementation part, is how to label the dominoes correctly so that no 2 neighboring dominoes have the same letter. In this case, one possibility is simply to use brute force in the sense when I'm labeling a domino, check all its neighboring squares, find the letter that is not present yet, and then use this letter. But there is a simple solution, and the simpler solution looks like this. For example, imagine that you take the entire rectangle and fill it with letters, for example, like this: A, B, C, D, E, F, and so on. So this is the alphabet. In the second row, take the alphabet but shift it by 5. and so on. In the next row, once again, take the alphabet and shift it by 5. So here would be Z and Y and X and so on. And now what you can do, each time you have a domino, take the letter in its upper left corner and use it in both places. So this is very easy to generate, and it can be easily seen that no two dominoes, if we use this pattern, no two neighbors will use the same letter because the same letters are sufficiently far apart from each other. So this was probably the easiest way to implement the last step. All right. Questions, comments? If not, then we can continue. All right. So, task number 5 on the farm. All right. So, the story behind this task is that this task is very popular in a much easier setting in primary schools. In Slovakia, I think almost everybody met the task that in the backyard you just have cows and chickens, and this is the number of heads, this is the number of legs, compute the number of cows and the number of chickens. And this is a really easy task, and for a long time I had the idea of trying to come up with a more general version that would be harder. So what I did, I started to randomly generate objects that can also have heads and wings and everything. And when I had the first few of them, I simply started to solve the task. And I found out that I like it. So in this way, quite randomly, a reasonably good task occurred. So in our task, what we have are 4 types of objects, which are in order of priority pianos, cabbages, chickens, and cows. And each of these objects may have some heads. There's a cabbage head, a chicken, and a cow has a head. A piano doesn't have a head. There are wings. A piano has got 1 wing. That's the open part on the top. A cabbage has no wings. A chicken has got 2 of them, and the cow has no wings, luckily. If cows did fly, I would probably be carrying an umbrella every day. And the last thing are legs. And the piano has 3 legs. A cabbage has no legs. Chicken has 2 of them, and the cow has 4. So, and right now, what we are given are the totals here. So we know the number of heads, number of wings, number of legs. And what we have to find out is the linear combination of these 4 vectors that does produce it. And in case there are multiple solutions, we have to minimize the number of pianos and then minimize the number of cabbages and so on. So what we now can realize from algebra is that if we take these as equations, so we got 4 variables. The unknowns are the number of pianos, cabbages, chickens, cows. And we get 3 equations. An equation for the number of heads. So 0 times A plus 1 times B plus 1 times C plus 1 times D has to be the given number of heads. We get a second equation here. We get a third equation here. So now, as the number of variables is larger than the number of equations, we get at least 1 degree of freedom. In other words, there surely has to be a linear combination of these 4 vectors that creates a 0 vector. So these are 4 different vectors in 3 dimensions. So one of them has to be linearly dependent on the others. So we can surely find the combination of A, B, C, and D. In this case, some of them may be negative, such that A times 0, 1, 3 plus B times 1, 0, 0 plus C times 1, 2, 2 plus D times 1, 0, 4 equals to the 0 vector. And this is actually something that can be useful to do right at the beginning, because anyway, we have, when there are multiple solutions, we have to find some of them, or some in some way specified solution. So we have to know something about how the solution space exists. Of course, there are other ways of solving this task. You can simply manipulate these equations and try to get exactly to the answer. And it is also possible to do it this way. But what I'm describing right now is my thought process when solving this task. So what I started first is try to find out this exact way in which these four vectors work together. And this is actually quite easy because, for example, you can start with a piano. You can see that the number of wings is odd, so you have to take at least 2 pianos. So we have 2 pianos, which gives us 0 heads, 2 wings, and 6 legs. In order to have 2 wings, you have to place a chicken on the other side of the scales, so to say. So you have a chicken here, which is 1 head, 2 wings, and 2 legs. So at this moment, the number of wings on the left, on the right is the same. Here we have 2 legs, or 6 legs, here's just 2, so we can add a cow here. Now the number of legs on both sides matches. The only thing left are the heads. So we take 2 more cabbages, and we get what we needed. So 2 heads on the left side, 2 heads on the right side. So what this means is that 2 pianos and 2 cabbages produce exactly the same set of properties as 1 chicken and 1 cow. And now seeing this, we are almost done, because clearly what we can do now, imagine that you have any valid solution. What I'm claiming is this: take a look at the numbers A and B. What we are trying to do, we are trying to minimize the number of pianos. So as long as A and B are both at least 2, we can decrease the number of pianos by 2, decrease the number of cabbages by 2, increase the number of chickens and cows by 1, and once again we would get a valid solution. So this means that the optimal solution has only 4 possibilities. And these 4 possibilities are A equals 0, A equals 1, B equals 0, or B equals 1. So we only have 4 cases. And in each of these 4 cases, what we will get, actually, is a set of 3 linear equations in 3 variables. And it turns out that in each case, this set of equations is actually regular. So it has just 1 valid solution in the reals, and this may or may not be a valid solution in the natural numbers. So in each case, we can easily solve this set of equations exactly and find out the answer. So the entire solution process is now, so we take the input equations, we substitute in turn each of these possibilities. So this will give us at most 4 candidates for the optimal solution, and we pick the best candidate, the lexicographically smallest one. And this leads to a solution that is pretty short, with not too many special cases, and quite easy to get right. All right, questions, comments? Great. Now let's get to the scary task, or one of the scary tasks, which is eating the pizza. This task looks pretty scary because it does clearly involve some college mathematics, but actually it turns out to be quite easy to implement, and it doesn't require anything non-standard if you consider it carefully. So the first thing we need to know in our solution, if we are given a pizza slice, the question is, where is the center of mass of a single pizza slice? And this can actually be computed in a numerical way, because we only need to do this once in our solution, so we can do quite a lot of computations, And even we can pre-compute this on our machine if we are scared, but it was not necessary. The only thing we need to do, we can take the pizza slice and we can cut it, starting at the center, into a bunch of very narrow triangles. And for each of these triangles, it is clear where its center of mass is. It's here, so it's the average of all the three coordinates. And in our case, we can simply say that if this radius is r, then the center of mass is located at 2/3 r times cosine of some angle phi and the sine of the same angle phi. And now we just run a cycle through 100,000 of such values, starting at 0 and ending at 2 pi divided by n. So we take 2 pi divided by n. In each case, we take this value to be equal, for example, to k over 100,000 times 2 pi over n. And we take k starting at 0.5 and ending at 99,999.5 or something like that. All right, so in this way, we can compute the center of mass of a single piece of pizza. You can actually verify in your program that the precision is sufficient by slightly changing the r. Because, when you are computing it with the original value of r, you are inscribing the smaller triangles. If you now increase r by some epsilon, you will be the circle will be inscribed into your triangles. So the first thing should be a lower bound, the other things should be an upper bound. You will actually find out if you do sufficiently many iterations that the numbers are almost exactly equal because of the precision of doubles. So this is precise enough. And once we know the center of mass for a single piece, we can compute the center of mass for any larger piece simply by averaging them. So if we know this point, we can rotate it here, and add them together. And this is something we can easily pre-compute. So in quadratic time, we can, for each connected part of the pizza, know the position of its center of mass. So this was all the mathematics needed in this problem. And the rest is pretty standard dynamic programming. The thing we need to realize is when we have two separate parts of pizza on the table, then we can solve each of these pieces separately, because the only thing we need to know to compute it, let's say that here are A pieces, this part contains B pieces, and if we only had this part, there would be WA ways of eating it. For this part separately, there are WB ways of eating it. So in the case we have both of these parts, what happens? In each step, we have to decide whether we will be eating a piece from the first part or a piece from the second part. So there are A plus B over A ways how to decide on this order of eating, to list a string that I will be eating from top, bottom, bottom, and so on. So there are A plus B over A such possibilities. And in each case, we can pick separately one of the WA orders of eating at the top and one of the WB orders of eating at the bottom. So whenever I get two disjoint pieces of pizza, I can solve each of them separately and then combine the answers into the answer for both pieces together. And this is basically everything we need to solve the task. Because what happens now is, in order to solve a piece of the pizza, we need to eat one of these pieces first. So we try all possibilities, which is the first piece eaten, and each time we picked and ate a piece, what we got are two new pieces of pizza, and we can solve each of these separately, and of course we can, for each of them, we first check whether it doesn't fall from the table. So in this case, in this way, we can solve each such sub-problem in linear time. So we have a pizza with n slices. This gives us quadratically many subproblems. Each subproblem is a connected piece of the pizza consisting of several consecutive segments. And now for each such subproblem, we can compute the optimal solution in linear time by checking each of the pieces at a time. So how many ways are there if this is the first piece I eat? How many ways are there if this is the one, if this, and so on? And if we pre-computed the binomial coefficients, then this can be done in linear time. So the overall time complexity is n cubed. Of course, we have to use memoization or dynamic programming. So we start with the smallest pieces and then build up the answers for the larger ones. And the resulting code is surprisingly short, and it's not so difficult to implement it once you get the right idea. All right. Questions, comments? All clear? Moving on. So, problem number 7 for today, finding the maximum. The gadget described in the problem statement is actually a theoretical construct that is quite well known and well researched, and it is called a sorting network. So we can represent the setting like this, and this is the way it is usually drawn in textbooks. So what we have are like wires, and each of these wires is carrying one of the input values. So at the beginning, this is the input array. And what we can use are so-called comparers or comparators. And each of the comparators is drawn like this. So each time we are like the numbers are traveling from the left to the right. And each time they meet the comparator, then they will be compared, these two values. And the larger one will go to the top, and the smaller one will go to the bottom, or vice versa. In our case, we are interested in the maximum, so the larger ones will go to the top. And now we are given the description of such a sorting network, and our goal is to check, first of all, whether it actually produces the maximum on the top wire, and if not, then we have to fix it in some way. So let's start with a basic question. How can we verify whether the maximum has to finish on the top wire? What we will be doing is we will be maintaining a set of wires where the maximum can be present. So at the beginning, what we know is the maximum can be anywhere, right? And now we will be processing the comparators from the left to the right, and each time we will update this set. So after this comparator, the maximum cannot be here, because if it was here, then it went up. After the second comparator, the maximum cannot be here, but it once again can be here, because if the maximum started here, then in this way it would get to this wire. And so on. So right now, we would end in this situation. So after these three comparators, we know that the maximum cannot be on this wire, it cannot be on this wire, but it can be on any of the others. And now all we need to do is we have to generalize this observation, because we are now trying to fix the sorting network. We will now have to add some new comparators. In this case, if we just want to make sure that the maximum will actually end on the first wire, what we need to do, for each other wire that can still contain the maximum, we need to add a new comparator that will go from this wire somewhere to the one of the upper wires. Because if the maximum can be here right now, and we don't want the maximum to be here at the end, we have to produce a way in order for the maximum to get away from this wire. So we need at least one comparator from this wire, at least one from this wire, and at least one from this wire. And quite obviously, we have nothing to lose by moving all of these to the topmost wire directly, because if we do this, then clearly the maximum will be transported to the top where we need it. So this would be a way of solving the task if there was no adversary, if you just had to fix the network. And the presence of the adversary doesn't really change too much. We just have to compute more general values. And in this case, what we will be computing will be the answer to the question, how many times does an adversary have to break a comparator in order to get the maximum to this wire? So in this case, these are basically the opposite values from the previous ones in case of an adversary who can break just one of them. So in this case, we will initialize all wires to a 0. So in order to get a maximum here, the adversary doesn't have to do anything. And so right now, we will be once again processing the given comparators one at a time. And what happens, each time we have a comparator, then in order to get a maximum here, the adversary has to break it. So he has to do this many breaks plus 1. Here there will be a 0. Now, in order to get the maximum here, once the adversary doesn't have to do anything, he can pick this number of values. So what happens in general, imagine we have a comparator like this, and the adversary had to do A actions in order to get the maximum here, and he had to do B actions in order to get the maximum here. So after this comparator, he needs B plus 1 actions in order to get the maximum to this wire, and he needs the minimum of A and B actions in order to get the maximum to this wire. So in this way, we can process the entire given input and compute this smallest number of edits for each of the wires. So once we get to the end of the given input, we have the information for the wires. So here it can be 1, a 7, a 2, a 3, and a 4, for example. And now let's say that K is equal to, or maybe 2. So the adversary is allowed to do at the most 2 actions. In this case, the wires with numbers larger than 2 are safe. So this wire is safe, this one is safe as well, and this one is safe as well. The adversary is not able to bring the maximum to this wire. And now for the remaining wires, the adversary needs already both of the actions in order to bring the maximum here. So if we now place one more comparator, we are sure that the maximum cannot stay here. For this wire, we would need to place 2 more comparators in order to make sure that the maximum cannot stay there. So this is what we do. We process the entire input. For each wire, we compute the minimal number of actions the adversary had to do in order to get the maximum here. And then we add the new comparators in such a number that we will force him to lose it anyway. All right. These sorting networks are actually a quite interesting and well-researched topic because they are closely related to sorting in parallel. If you take any such sorting network that actually sorts, so it means that regardless of the order of inputs, the outputs will be completely sorted, then each such sorting network can easily be turned into a sorting algorithm. And moreover, this algorithm is very easy to do in parallel because if you have comparators that use disjoint wires, you can do these comparisons and necessary swaps at the same time. So there is actually, there are sorting networks known already that have just logarithmic depth. And this corresponds to an n-log n sorting algorithm that can, in addition to this, can be easily parallelized and done on multiple machines efficiently. So this is quite an interesting topic, and if you haven't seen it so far, I recommend studying it. I believe it is also described in one chapter in the CLRS textbook, so you can find it there. One interesting topic about these sorting networks is the so-called 0-1 theorem, which says that, well, imagine that you have a completely unknown sorting network and you want to test it, whether it sorts all the possible inputs. Then one of the brute force solution would be to try all permutations of values 1 through n as the input. And if it sorts each of the permutations, then it is correct. And the 0-1 theorem says that in order to test such a network, you don't have to do this. And it is enough to test all the 0-1 vectors. So not n the factorial of n, but just 2 to the n of possible inputs. All right, and now for the last task, which is the vacuum cleaner. And this is quite obviously a task motivated by a friend of mine buying the Roomba vacuum cleaner. It's quite entertaining to watch. And the idea for the problem came from this. So let's start with analyzing the problem statement. So what we are given is a flat which contains some rooms and some corridors between those rooms. And moreover, it is promised that the number of rooms n is less than or equal to 8. And in addition to that, it is guaranteed that the graph is planar. What information does the planarity give us? The information that is crucial to solving this problem is that the number of edges of corridors is small. If we consider any planar graph, what can be done with the planar graph? You can add new edges to a planar graph. For example, like this. Now a new edge here, and a new edge here. And one more is possible, and this is this one. And now we are done. So you can do this with any planar graph, add edges greedily while is it possible. And when it is not possible anymore, what you get is a so-called planar triangulation. So each of the faces is a triangle, and this is the reason why you cannot add any more edges, because the triangle has no diagonals. So, and if you have a planar triangulation, you can very easily compute the number of edges, because there is the Euler formula which says the number of vertices plus the number of faces is equal to the number of edges plus 2, or in general, number of edges plus the number of components plus 1, if the graph is allowed to be disconnected. And in this case, we know that each of the faces is a triangle, so the number of edges can be computed as 3 times the number of faces, and this has to be divided by 2 because we count each edge twice. And from this we can get to the conclusion that the number of edges is 3 times the number of vertices minus 6. And this is valid for all graphs with more than 3 vertices, or more than 2 vertices. For 2 vertices, there is a graph with 2 vertices and a single edge as a special case. So as long as the number of vertices is at least 3, then this is the formula for the maximum number of edges in a planar graph. What it gives us for n equals 8 is that the number of edges is less than or equal to 18. So now we have some process, and the process is continuous. So the first thing towards solving the task is to change the process from a continuous one into a discrete one, which happens in some steps. And the steps will actually be cleaning the entire room, cleaning the entire corridor. So, for example, one thing we can do is we will call a state, will be a situation immediately after cleaning a room. So the states are exactly the moments when the vacuum cleaner makes a decision, which corridor should I choose next. And now what we need to do, we need to describe the state. And we need to pick a description that is as short as possible. In this case, what we need to describe a state are just two things. The set of clean edges and the current room. The thing to note here is to realize that we don't actually need to store the set of clean rooms, because the set of clean rooms can be deduced from the set of clean edges in the current room. So this is all we need to describe a state. And at this moment we can compute the number of states. There are 2 to the 18 possibilities for the set of clean edges, because each of the edges can be either clean or dirty. And this is basically 250,000. And there are 8 possibilities for the current room, which gives us roughly 2 million states. Many of these states will actually not be reachable, because the current room has to be one of the rooms that are clean. So the actual number of reachable states will be much lower than this. But still, an upper bound of 2 million is a good thing to have. It tells us we are possibly on the right track. So right now, what we need to do is we need to find a way how to compute an answer for a given state. So for what we will be doing is quite standard in tasks like this one, when they ask you for an expected time until something happens. We'll be using dynamic programming, or more easily to implement a recursion with memoization, where for each possible state we will compute the same answer. What is the expected time from this state until the entire flat is clean? So if we now imagine some state, so we have a set of edges that are already clean, for example these 3, and we have a current room, for example we are here. So this is one possible state we can be in. And also there are several other states that use exactly the same edges, which is the state when we are here, when we are here, and when we are here. So these are 4 states that are very closely related, and we will compute the answer for these 4 states at the same time. What we will do, we will have a variable for each of the states. So we will have a variable, for example, x1, x2, x3, and x4. So this x4 is the variable saying what is the expected time until the entire flat is clean if I already cleaned these edges and I'm currently in this room. So we have, in this case, 4 variables. At most, we will have 8 variables, because 1 per each room. And now for each room, we can write a linear equation in the standard ways. This is done with expectations. So for example, for this room, x1, we get the equation that, what is x1? With probability 1/2, I will choose this corridor to clean next. And in this case, I have to pay the time to clean this corridor. This can be like the time L1. Plus, I have to clean this room. This can be like the time T3, let's say. And plus, I then have to pay x3 to clean the rest of the flat. So this is the first choice. If in this state that is described by the variable x1, if I pick this corridor, then the total time it will take me will be this time for cleaning the corridor, plus the time for cleaning the room, plus x3, which is the variable saying how much time I need on average if I start here and have these edges clear. And the other thing, in other 50% of cases, I will pick this edge, and in this case, I will pay the cost for this edge, which can be like L7. I will pay the cost for this room, which can be, let's say, T2. And plus, I will now pay some other cost. And what is this other cost? This other cost is the answer for some different state. And the new state is I am in the room x2, or well, in the room 2. but the set of clean edges already contains this edge as well. So this is another state, and the thing to note here is that the number of clean edges always increases. So what we can do is we can make a recursive call in order to find out this value. And when we get the answer back from the recursion, we can just plug it into this equation. So what we will get in this way, we will get a set of 4 linear equations for these 4 variables, and we can then use Gaussian elimination to compute the actual values, and this is quite obviously always possible. So this is what happens during the solving process. We have a recursive function, compute the answer for this state, and the function does it produces all the equivalent states, it produces the set of equations, it makes recursive calls for the new states with more clean edges it needs, and it then computes the answers from this small set of equations and returns the answer back to the parent. And that's basically all there is to this task. The terminating conditions are the only tricky thing to handle, then, because you need to, when you are getting close to the end, when the current state already has almost all edges clear, what you need to do is, for example, in this state, if I were to pick, so this is the state, I'm here, and these edges are all clear. If I were to pick this edge, then I have to pay the time to clean the edge, the time to clean the vertex, and then I'm done. But it is also possible, for example, if I'm in this state, that I'm in this vertex, and these are the clean edges, then all vertices have already been cleared. So in this case, if I pick this edge, I will just pay the cost for the edge. I will not pay the cost for the vertex anymore, because as soon as I clear the edge, I'm done. So these are the 2 cases that need to be distinguished at the end, and this is a place where one has to be a bit careful, but other than that, it's everything. All right. Any questions or comments about this one? If not, then thanks for your attention. Yeah, okay, one question.
Well, I bet everyone here has a question, but I don't even know what to ask you. On the equations you have x1 depending on x3. When you have x3 depending on x1, well, I don't get it. You have 4 equations with more than 4 variables, because you have x1, x3, then y, y1, y3. How do you handle this?
Well, actually, what you do, the only actual variables at the moment when you will be solving the set of equations will be the variables for the currently considered states with the fixed set of clean edges, because each of the y's you need is computed before actually solving the equations. So whenever you find out that you need the answer for some other state, for a state that contains more clean edges, at this moment you make the recursive call. The recursive call will compute the answer and return it back to you, and you can then take this actual number and plug the actual number into the equation. So the only variables will be the ones corresponding to the current states, to the current number of edges. If you prefer the dynamic programming point of view, then you can view this solution like this. At the beginning, we can compute that the answer, if all edges are clear, is 0. Then we will consider all subgraphs with 17 edges. Then we will consider all subgraphs with 16 edges, and so on. At the moment, when you are considering subgraphs with, for example, 3 edges, like it was drawn in the beginning, or maybe, so this was the original picture, like this. So we have these 3 edges are clean. Then you already know the answer for all states that have more clean edges. So if you take a decision here to go along this edge, you then immediately know the answer for the new state, and you can use it. So the only unknown variables at this time are the answers for these 4 states. So these are the clean edges, and I'm here, 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 or here. And one more thing I can add right now is a rationale why this system of equations always has a unique solution. you can imagine a process that you are actually simulating what the vacuum cleaner does. So for some time it will be moving along the sets and along the set of clean edges, and sooner or later it will visit a new edge. And this happens with a constant probability. So if you compute for each of the states the probability that it is currently in the state, then these probabilities have to decrease, and they have to decrease in a geometric fashion. So this process converges always to the correct answer. This is basically the same thing as if you are flipping a coin and waiting for the tail. This will always happen. Well, the expected number of flips will always be constant, and the same thing here. The expected number of moves until you visit a new edge is always a constant, and that's why it always converges. And the system of equations will then, without the need for simulation, it will directly compute the expected times. All right. Okay, so I think that's all, and thanks for your attention.